Hey everybody, this video is about power. So really quickly, power is defined as, power, P, is the time derivative of work. That's it. Right, and then the units for work, joules. So the units for power, joules per second, which we call a watt. Okay. That's it. Notice that work is, you can define it as like F dot this force dot displacement. Right, so for work, you can define it as force dot displacement. So power is work as a derivative with respect to time. So if you take a look at this, we can take this part of it and then F dot dr dt. Dr dt meaning the time derivative of position, which is velocity. So like this, time derivative, or power is force dot velocity. Okay, that's it. So that was straightforward. Let's do a quick example here. There's an example out of the book. So we have this car going up a hill. So let's stray from it a little bit. Let's say the car goes 90 kilometers per hour. And let's say it drives for 1 minute. So let's say we got 60 minutes in an hour, and then let's say you go for 1 minute. 1 minute. So how far do you go, the displacement? So let's just call it d. Right, so that's going to be 1.5 kilometers. So you go up the hill 1.5 kilometers. How much work is being done by gravity? Try that out for practice. Right, so then if we know the incline, 15% means for every 100 of these you get 15 of these. Right, so whatever it is, feet, meters, miles, that's the ratio. So then the angle has got to be arctan opposite over adjacent. Okay, so we know the angle. We know the hypotenuse, which means you know this vertical component of the displacement. I'll just call it some height h. And we know the mass of the car. So we know the weight is this way, mg. So we know this force and this displacement. So the displacement is this way horizontally, this way vertically. This force dot this component of the displacement is 0 because they're perpendicular. But then this dot this would be negative. Right, so if the car goes up the ramp 1.5 kilometers along the hypotenuse, then we know that this would be, so the work would be mg, and then with a minus sign, d sine theta, right? So it'll be negative, the work by gravity. Now what if the car were driving 9 kilometers per hour for 10 minutes? So 9 kilometers per hour for 10 minutes. Then it would still go 1.5 kilometers, but it will just take 10 times longer because it's driving 10 times slower. Now what is the work when the car goes up the ramp? Still this much. Right, so the work has nothing to do with how long it takes or how fast the car is going. Just the displacement and then the weight of the car. So keep that in mind. Now for the power, right, we just got, let's read this a little bit more carefully. So we know the speed, and then let's assume 25% of the power is overcoming air resistance and friction, meaning 75% of the power, 0.75 of the power is into overcoming gravity, basically. Okay, so the displacement is this way, displacement. The weight is this way, weight. So we need F dot V. So what is the force we can decompose? So let's say I pick coordinates like this. So then the velocity is along the x-axis, and then we know the number, right? 90 kilometers per hour. So that's 90 kilometers per hour in the I direction because of the way I pick my coordinates. And then for the weight, angle is here. So that would be in the x direction, negative sine, and in the y direction, negative. Okay, so let me write it like this. So when we take the dot product, this times this plus this times this equals a scalar in watts. Okay, and so then if you want, and that's only 75% of the power, so that will just take this and move it in the denominator here. Then you know the power for the car to go up the ramp, and notice that it does indeed matter how fast the car is going. The faster it goes, the more power it needs. Okay, so give this a try, and then let me know if you have questions, and I'll see you on the next video.